Alright, welcome to Chapter 5, our last chapter in the semester. We're going to be working with systems of linear equations, and also in the next section we'll be talking about systems of linear inequalities, as well as just linear inequalities. So, many applications in the real world deal with linear models. Many times, two of those linear models are put together to form a system of linear equations. Now, all equations in the form, and we're going to do the standard form, ax plus by equals c, are straight lines with graph. Two such equations are called a system of linear equations, or just a linear system. Now, a solution or an answer to this system of two equations and two variables is the ordered pair that satisfies both equations. So we will write our answers in that xy ordered pair. So let's look at this first example to determine if each ordered pair is a solution to the system. Now remember, this is our xy point, and here is our system of equations with two variables, with two equations. And so basically we're going to do a substitution. We're going to take the x equaling 1 and place it here, the y equaling 2, place it there, and see if we get a true statement. So just by substitution, I'm going to do 2 times 1 minus 3 times 2. And I'm going to ask the question, is that equal to this negative 4? Well, by order of operations, we would multiply, then subtract, and we do get negative 4. 2 minus 6 is a negative 4. So we also want to do that same thing with the second equation. So it has to be a true statement for both equations for it to be a solution. If only one of them works, then it is not a solution for the entire system. So let's plug that 1 and 2 into the 2x plus y equals 4. We would get 2 times 1 plus the y value. Is that equal to 4 in question? Well, that's 2 plus 2 definitely is 4. So yes, since both of them worked, this is a solution to our system. If I were then to try this xy point, 7, 6, to see if it's a solution in our equation, I'm going to again plug it right in here. So let's do it in the first one, where I would do 2 times 7 minus 3 times 6, and is that negative 4? Well, here is 14, here is 18. When I subtract them, then yes, I do get negative 4. It works. But when I plug negative 7 and 6 into the next one, does it work? Well, I get 2 times 7 plus the y value. Is that equal to positive 4? Well, this is 14. That is 6. Is that equal to 4? Absolutely not. So no, this would not be a solution to that system. Okay? So the point has to work on both of them. Now, what does it mean by the point to work on both of them? Let's visually look at what we're doing when we have two lines here. And graphically, what do we know about systems? There's three possibilities. One in which we call intersecting. The second would be parallel lines. And the third would be what we call coinciding lines. Now, what are intersecting lines? Well, those are defined to be two lines that cross. So there's two intersecting lines. And the idea of the solution for a linear system are the points that the lines have in common. So common points. Well, in this case, there's my common point. So therefore, this would have one solution, call it x comma y, as our answer for that system. If we have two parallel lines, which look like this, how many points do they have in common? Well, the definition of a parallel line, or parallel lines, mean that they do not intersect. Therefore, there are no or none, no solutions in this case. You could also write it as the empty set if you so chose. And then our coinciding lines are basically two lines, two of the same lines, but they look like different lines with the equation. If you just multiply any equation by a number, you get what we refer to as coinciding lines with a system. So there would be an infinite amount of solutions, And we would write that solution as all points xy such that, with our colon, that we are on the line ax plus by equals c. Or you can do y equals mx plus b. I don't care how the form you have on those lines. Either way works. It just states that you want all the points on that line. Alright, so those are special cases, those last two. Most of the time, we are going to be looking at those that are intersecting when we're solving our systems. Alright, so what are those three ways? The three ways are, the board was frozen a minute. We are going to do it by graphing. We are going to solve a system by what we refer to as substitution. And we are going to solve them by what they call as the adding method. And that adding method is also sometimes referred to as elimination. So I can see why they say that both times. We'll talk about that whenever we get there. So let's first do by graphing. When we solve a linear system by graphing, we're looking for that intersection point, or we're looking for those parallel lines to say that there are no solutions. In order to do that, to graph the lines, we want to put each of our lines in our nice y equals mx plus b form. Once we have that, then we can graph our equations, and in step 3, we can find the intersection point. So therefore, our answer is some xy point. Okay? So let's look at each one of these equations. I'm going to start with this first one. To get y by itself, we've done this numerous times before, I'll have to get rid of that x. So I'm going to subtract x and let y equal negative x plus 2. As a reminder, this is my y-intercept. And that number in front of x in this case is our slope. It is a -1. Most of the time those slopes are written as fractions, so we can do our rise over our run in order to graph that. Okay? Now, let's look at this next equation. In order to get y by itself, I'm again going to subtract x. And I get negative 3y equals negative x plus 6. When I then divide by negative 3 in each case, then this goes away, and I'm left with y equals. Now, when I come to this piece, remember there's a 1 in front, and I'm going to extract out that whole number in front of the x. Now, to reduce that, remember to get rid of your negatives to make it a positive 1/3 x. Positive 6 divided by negative 3 is a -2. So this is the equation I want to graph, and that is the equation I want to graph. Let's first start with this one. We're going to go to the y-intercept of 2. Then I'm going to do my -1 over 1 with my rise over run. So I go down 1 over 1, down 1 over 1, down 1 over 1, and notice that it is a declining line, decreasing line left to right. I like to extend all those points through my grid when I'm working with systems. That doesn't work very nicely, because then I can get that intersection point very accurately. Okay, let's now graph this guy. So 1/3 x minus 2, that -2 means I have an intercept on the y-axis of -2. Then I'm going to go up 1 and over 3, and I actually get that point, ding, 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 on that line. If I wanted to continue the pattern on my grid, I could go down 1 and to the left 3, and I end up completing my system by graphing. And now we can identify this point right here as 3, -1. That is the solution that we are searching for. The intersection point for that. Okay? Alright. Let's now turn to substitution. Substitution is the second way we're going to solve a linear system. And we are going to first, number 1, you have to get x equal or y equal by themselves for number 1 in order for substitution to work. Doesn't matter which one, just get x equal or y equal to if they're not giving it to you to be good with. Now, number 2, we want to substitute the expression found in step 1 into the other equation. After that, we have an equation that only has one letter in it, so we're going to solve that equation in step 3, and we're going to substitute that answer in step 3 back into one of the original equations to find the variable. again, our answers are going to be x, y points. All right, so let's look at this example. Notice in one of those equations, I do have y equals by itself. That's a very nice way to start a substitution problem, because the idea is in our second equation, in this case the top one, I'm going to take out wherever this letter is that I have by itself. I'm going to take out the y, and I'm going to plug in what I have for what y equals to in the second equation. So what that looks like then is I need to rewrite that 2x minus 3. Now that's where my y was. I'm going to put all of this in there as a 2x plus 7 equals that negative 13. And now I have an equation with just one letter that we've done multiple times on how to solve. So I want to distribute first and get 2x minus 6x minus 21 equals negative 13. Then we must combine like terms on the left side to get a minus 4x minus 21 equals negative 13. Then I'm going to add 21 to both sides. That goes away. Negative 4x equals an 8. And when we divide by the number next to the letter, therefore x equals a negative 2. Now that's half of my point. Remember, we had an ordered pair. So it's going to be negative 2 comma something. Well, what is that something? We solved our equation. Now we have to sub that back in and find out what y equals. In order to do that, I'm coming right back to this equation. It explicitly told me that y equals take 2 times the x value and add 7. So y is found by taking 2 times the x value that we found down here and adding 7. So y here is negative 4 plus 7, which is 3. So negative 2, 3 would be our final answer for that solution. Okay? All right. Now let's determine what we have in this next system. This next system definitely doesn't look like the first one because I don't have x equal or y equal by itself, but I can get one there very nicely. So I do have a coefficient of 1 right here that I'm honing in on any substitution problem, just because it's very nice to get that y by itself. If you were to try to work with the first equation, you're going to end up with lots of fractions, and that's not always nice. So I'm going to first subtract 2x from both sides. That goes away. And normally with our lines, we write it as negative 2x plus 1. But I like to, with substitution, go ahead and just keep my negative in the back. So this is the equation now that I've transformed from here. So in the next equation, or the first equation this time, I'm going to find this variable. I'm going to take that out, and I'm going to plug in what it's equal to right into there. So I'm going to substitute that expression in. So I'm going to start and rewrite all of that equation as 3x plus 2. Take out the y and replace it with what it's equal to. Has to equal 4. And again, just like last time, we end up having an equation that we can solve. Let's distribute our 2 to get 3x plus 2 minus 4x equals 4. Combine your like terms, gives you a minus x plus 2 equals 4. Subtract 2 gives me negative x equals 2. And you can divide by negative 1 if you want, or just change the signs to make that a positive x, okay? So x equals negative 2. Again, my solution is going to be the point negative 2 comma something. I have to figure out that something. What is that something? I can plug it here, I can plug it here, or I can plug it here. I'm actually going right there because it tells me y equals 1 minus 2 times that x value, which was negative 2. So 1 minus 2 times the negative 2, that becomes a plus 4. And that's what y equals to with a 1 plus 4, which is a 5. So negative 2, 5 is my solution for this system. Okay, so lots of little pieces. Make sure you can kind of follow along with that process. Go to those step-by-step pieces and solve the system. All right, our next one is solving systems by addition method or the adding method, and it's also called the elimination method. So, if necessary, rewrite both equations of this standard form, ax plus by equals c. Now, you don't have to methodically do that every single time. As long as your x's, your y's, and your numbers, and also your equals are lined up, then you are good to go. Now, if necessary, we are going to multiply either equation or both equations by the appropriate non-zero numbers so that the sum of the x coefficients or the y coefficients is 0. So we want to eliminate a variable. After we have that, we are then going to add our two equations together. That will create an equation with one variable that we are going to solve in step 4. Then we're going to substitute that number that we received in step 4 into any other of the equations to solve for the other variable. So let's look at what we have. Notice these two equations. We have the x's lined up, we have the y's lined up, the equals lined up, and the numbers lined up. Okay? So we are going to then see if our x's or our y's will go to 0 if I add the coefficients. Now the numbers out front. So if I take 3 plus 3, does that give me 0? No, it does not. If I take positive 2 plus a negative 2, or 2 minus 2, does that go to 0? And the answer is yes, okay? So those are going to be the variables that we eliminate out in order to get our equation with one letter in it. So once we can verify this piece, we are going to add these two equations together. I'm going to do this as an elimination, or canceling itself out. So therefore, 3x plus 3x is 6x. Bring your equals straight down. And add the 14 and 10 to give us 24. Now it's a one-step equation that we divide by 6 both times and get x equals 4. Now remember, again, how many times have we said this? For something, some number is going to be our solution. So we need to make sure that we plug 4 in to one of those equations for x. I'm going to choose this very first one. It doesn't matter. I like to have that positive y value there. It's up to you. So wherever I see an x, I'm going to put a 4. So I get 3 times the 4 that we found right here, plus 2y equals 14. Then I'm going to multiply to get 12 plus 2y equals 14. Then I'm going to subtract 12 from both sides. And we get 2y equals 2. Therefore, y equals 1. So that is the final piece in my point for my solution. Okay? Now, it's nice if we can just add them directly and something goes away, but not all the time will that happen. If I try to add these, I get 6x. If I try to add these, I get 2y. Unfortunately, neither one of those are 0. So that's where we come into play on step number 2, where we have to multiply either equation or both by an appropriate number for them to go away. Well, if we look at our x values, it would be nice if we can make a common number. Now, we could do that by looking at making both of them 8s and then one of them to be negative. But I always look at the smaller one and I say, okay, can I multiply this by something nice to get 4? And it is true. I can multiply 2 by 2 to get 4, so that's nice. Can I multiply 3 by something nice to get 5? And the answer is no. 3 won't go evenly into 5, so that is why that answer is no. So in order to make this occur to where I can get the same number here, I want to make sure that I'm able to do that in an opposite form, okay? So if I were to multiply by 2, that's going to give me a positive 4. But I don't want to do 4 plus 4. That's not going to give me 0. I want that to be a negative 4. So I have to be able to bring in a negative number there. Okay? So I'm going to keep that 4x plus 5y equals 3 steady. Then I'm going to distribute this negative 2 to each one of those as negative 4x plus 6y equals a negative 14. The common mistake is that you forget to multiply the end number by that number out front. okay? So at this point, we are able to now, yes, when I add my two equations together, I can eliminate the x's, which is very nice. Because now when I add 5y plus 6y, I get 11y. And I do 3 plus a negative 14 gives me negative 11. And when I divide by 11, my y value is negative 1. So here's the half of my point. Y is negative 1. We're out to find x. Now, remind you have this equation, you have the inside piece here, that equation, and we have this equation that we created new by multiplying by negative 2 to plug that negative 1 in. I'm going back to the original, okay? I just sometimes do that. There's no rhyme or reason for it. I just kind of go back to the original. So I'm going to place negative 1 in for y. So I'm going to start with 4x plus 5 times the negative 1 for y equals 3. So I multiply positive 5 times negative 1 gives me a negative 5 equals 3. And I'm 2 steps away to get my x. So when I add 5, I get 4x equals 8 and x equals 2. Therefore, the solution for this system is 2, negative 1. Okay? All right, moving right along on our last page here for section 5.1. Let's do one more of these, and we're going to hit a special case, and then we actually have a couple word problems. So notice in this equation, or this system, that we don't have anything nice on the little numbers that we can multiply to get our bigger number this time. Nothing that you multiply nicely by 3 to get 5. Nothing that you multiply nicely by to get 9. So unfortunately, when that occurs, you have to change both equations. So the idea is that these numbers have to be opposites. We have to form with a common multiple of what those numbers are. Well, a common multiple between 3 and 5. What's the smallest number that 3 and 5 can go into? It would be 15. What is the smallest number that 4 and 9 will go into? And I believe that number would be 36. So if I can force those to be the same number and more specifically opposites, then we can eliminate those variables, okay? So I'm going to work with the 3 and 5 just because it's smaller to get the common number is 15. So if I'm going to need a 15, I need a 5 for that first one. When I multiply by 3x, I get 15x. And this one, I need a 3, but one of those has to be negative. Doesn't matter which one is negative. You can do it on the first one or the second one. Just pick one. So now when we distribute, I'm going to draw a line so we know where it's separated. I'm going to distribute that 5 all the way through as 15x plus 20y equals 10. And when I distribute my negative 3 through, I get negative 15x. Negative 3 times negative 9 is a negative 27y. And that equals a positive 18 when I multiply by negative 6. So now when I try to add these two equations, look what happens. Those x's go away, and I want to combine my y's. 20y minus 27 is a minus 7y, and 10 plus 18 gives me a 28. When I divide by negative 7, therefore y equals negative 4. So that is half of my point. I have an x value that I have to find, and we already have our y value. So now you actually have 1, 2, 3, 4 equations to plug that into. Again, I always resort to go back to the smallest number one. So I'm going to place that in for y. So I get 3x plus 4 times a negative 4 equals 2. So 3x, this becomes a minus 16 equals 2. When I add 16 to 2, I get 18. And when I divide by 3, I do get 6. Therefore, 6 negative 2 is my answer. Okay? So that's all the different possibilities for elimination. And I will tell you, most often than not, you will be solving a system by elimination. All right. Let's do our special case. Our special case says x minus 4y equals negative 8. 5x minus 20y equals negative 40. So if I'm looking to eliminate the x's or eliminate the y's, I definitely don't have opposites on each of those. So we have to get it there, okay? I'm honing in on this 1 right here. I can make that anything that I want. Since this is a positive 5x, I would have to have the opposite up there for those to eliminate. The opposite of that would be negative 5. So if I multiply the top by negative 5, I get negative 5x plus 20y equals positive 40. Now I'm just going to rewrite that second equation as 5x minus 20y equals negative 40. Now I'm ready to go because my x's go away when I add those two equations. But what happens also to my y's? 20y minus 20y also goes away. So technically both of those go to 0 on the left side. And look what I have here. 40 minus 40 is 0 as well. Now notice our x's and y's go away, so we can't really solve for x and y to create a point. What we have here is a true statement. If we have a true statement, that means our special cases are either our coinciding lines or our parallel lines. This is the case where it is those coinciding lines, and we have infinite number of solutions. So we have all the xy points such that, now pick one equation, I don't care which one, let's go back to this original, such that x minus 4y has to equal negative 8. That's how we would write our solution. So those are those two lines that are basically the same line, it's just a different equation. It's actually just a multiple of the other equation. Okay? So here, what happens if we have coinciding lines? You get a true statement in which we write all xy such that ax plus by equals c. Or, I'm okay with you even just doing the mx plus b form. As long as you just have one of those equations, you should be fine. Now, what happens if our statement up here that we have is incorrect? Like I get 0 equals 4 or 5 equals 10. Those are false statements. And if we have a false statement, that's when we have those parallel lines and our solution is the empty set. Nothing is in common when we have those parallel lines. Okay, so intersecting we have the point. Parallel, there's no solution. Coinciding lines, there's infinite solutions for our system. Alright, so our last two examples deal with word problems. And the hardest part of word problems and systems is actually getting the equation. I think after you practice solving the systems, you'll get the hang of those. The hard part on these is getting the equation. So as a reminder, there's keywords in here that we want to look at. Sum means to add, is means equals. Here it talks about subtracted and the difference. So making sure you're picking out keywords to help. Or create an example like we will kind of down here to get you to think about what needs to happen. So I come to this first sentence and it says the sum of two numbers is 2. It also then states that if one number is subtracted from the other, their difference is 8. We want to find the numbers. So we have to let some designation be our x and our y. These are our unknowns. So I'm going to let x be my first number and y be my second number. So if I go to my first statement and it says the sum of those two numbers, the sum of x and y is 2, to sum something, that means we have to add those two things together. So that means that I have to add x and y, is the equals 2. There's one equation. But I can't have it all by itself because with two letters we have to have two equations. So I come to this next one, it says their difference is 8 when I subtract them. So if I subtract these two numbers, then x minus y is equals 8. And now we have a system. We have everything lined up, which is nice. X's, Y's, and numbers. We can go ahead, I would do elimination, just because what happens right there, they are nicely gone. So I have 1x plus 1x, which is 2x, equals 2 plus 8, which is 10, dividing by 2, x equals 5. So that's my first number. That's one solution. The next solution, I have to find by plugging that x equaling 5 in. So we're going to take this, and I'm going to plug it right into this original. So I take x plus y equals 2, or 5 plus y equals 2 when I sub it in. And when I subtract 5 from both sides, y equals negative 3. So that's the other number. That's my second number. And so this is how some students have left me as a solution. Others have done it in braces since it's just numbers. What are my two numbers? They're 5, negative 3. I would take it like this also. You gave me the numbers 5, negative 3. Those are your two numbers. So multiple ways to write your answer for your word problems. But on this instance, we actually have a meaning here of these. Okay? We're not just asking for numbers. We have a real world example. And it talks about a local buffet charges $7.50 per person for a basic buffet and $9.25 for a deluxe buffet, which includes crab legs. If 27 diners went out to eat and the total bill was $22.27 before taxes, how many chose the basic buffet and how many chose the deluxe buffet? Now, the idea also for variables, you can use x, y all day long if you want. Sometimes in math, we like to use letters that designate what we're talking about. So in this case, maybe B would be a good letter to use for the number of basic buffets, and D be the number of deluxe buffets. And so then when I solve for my letters, I know B stands for basic and D is for deluxe. So let's say I have two people that are ordered buffet, basic buffet, and 5 that ordered the deluxe buffet. If I asked you to give me my total, what would you do? Well, 2 people at $7.50 means I could multiply those together, and then I could also multiply 5 by that $9.25 to figure out how much that costs just for the deluxe. And then in order to do that, so we would multiply, to find my total, we would add those two things together, okay? So getting you to think, I did that specific situation just for you to think about what we need to do. We need to multiply. These are the things we're looking for. How many basic, how many deluxe did we sell? So instead of 2, now I'm going to take that out and I'm going to say, okay, that's B. I don't know what it is. And this is D. So I'm still going to times those two together, which can be represented by 7.5B. And I can times these two together, which is represented by 925D. To find the total, I have to add them up to get how much it was. Well, right here is how much it was. And I'm going to do 227. So that's one equation. But the second equation has to come from the other piece that I don't really have in my problem yet. The other piece said that I had 27 diners. Well, let's go back to the example that I started with. If I had 2 people order the basic and 5 people order the deluxe, how many people were with me? Well, that would be 7. I have 2 plus 5 gives me 7, right? Well, I take that out. I don't know what that is. That we represented as B for my basic and D for my deluxe. And if I'm adding those two together to get my total number of people, that's what I have right there. So B plus D has to equal 27. And that right there is the system that we need to solve. Now, in order to solve that system, it's going to be very nice. You can do it by elimination. This is one that could possibly be a nice one by substitution. But I'm going to do it by elimination because I'm going to use the smaller one. If I could have a negative 7.5 right here, then I would be able to get a variable that is eliminated. So I'm going to start with the first one and rewrite it. 7.5b plus 9.25d equals 227. Then I'm going to distribute this negative 7.5 minus 7.5d. And when I multiply negative 7.5 times that, I get negative 202.5. And now we're ready to add them. Namely, these two are going to go away. When I combine 9.25 minus 7.5, I get 1.75d. equals 24.5. And when I divide by 1.75, that goes away. D here is 14. So what does that mean? I had 14 deluxe diners. 14 people wanted the crab legs on the deluxe buffet. So how do we find the number of basic? Well, again, I've got 1, 2, 3 equations I can plug that into that are different. I'm going to choose the easiest and plug it into this pink one and put that in for D. So that means that B plus 14 has to equal 27, and when I subtract 14, I get 13, and that's how many basics that we have. So that would complete my problem for what they are asking in this sense. So again, it's so much easier to solve this system once you practice it. The hard part on word problems is that you have to set it up first. But no fear, I have confidence that you can pick those keywords out, you can do a specific case, and you can get those equations. So until next time, we're in section 5.5. We're going to talk about linear inequalities as well as systems using those as well as also some non-inequalities and non-linear systems in section 5.5. So until next time.